Right now, the fastest spacecraft humanity has ever launched is moving away from Earth at a speed that makes every previous human achievement of velocity look like standing still. The Parker Solar Probe, during its closest approach to the Sun, reaches 430,000 miles per hour. To understand what that number means in human terms, consider this. At that velocity, you could circle the entire circumference of Earth, all 24,900 miles of it, in under 4 minutes. You could cross the continental United States from the Atlantic coast to the Pacific in roughly 20 seconds. Standing at the edge of a runway watching a passenger aircraft take off at 500 miles per hour, the Parker Solar Probe would be gone before your eye could register that it had appeared. It is the fastest thing humans have ever built. It represents the absolute pinnacle of what our species can currently achieve in terms of raw mechanical velocity. And yet, measured against the scale of what actually needs to be crossed to reach even our nearest neighbouring star, it is almost nothing at all. The nearest star to our Sun is Proxima Centauri. It sits at a distance of 4.24 light-years, meaning that light itself, the fastest thing permitted to exist in this universe, travelling at 186,000 miles per second, takes 4 years, 2 months, and roughly 2 weeks to make the crossing. In miles, that distance is approximately 24.9 trillion. Written out fully, that number looks like this: 24,900 billion miles. When you put the Parker Solar Probe on that track, the fastest thing we have ever built, moving at 430,000 miles per hour, the math becomes quietly devastating. The journey to Proxima Centauri at Parker Solar Probe speed would take approximately 6,400 years. Not 600, not 60, 6,400 years. That is longer than all of recorded human civilization. Longer than the pyramids have been standing. Longer than the entire gap between ancient Sumer and the present moment. The nearest star is, by any honest measure, impossibly far away with every technology our species currently possesses. To make this even more concrete, consider the Voyager 1 spacecraft. Launched in 1977, Voyager 1 has been travelling away from Earth for nearly 5 decades. It is currently the most distant human-made object in existence, sitting at roughly 15 billion miles from the Sun, so far away that the radio signals it sends back to Earth, travelling at the speed of light, take more than 22 hours to arrive. By any standard of Earth-based experience, Voyager 1 is extraordinarily distant, and yet in terms of interstellar travel it has barely moved. 15 billion miles sounds enormous until you calculate what fraction of the distance to Proxima Centauri it represents, less than 0.2%. At Voyager 1's current speed of about 38,000 miles per hour, which is itself faster than almost anything in human experience, the spacecraft will not reach Proxima Centauri for approximately 73,000 years. It is also travelling in the wrong direction, but the principle stands. The scale of interstellar space makes our fastest achievements look like someone walking across a parking lot and calling it a continent. This is the central paradox of human spaceflight in the 21st century. We live in an era when humans have walked on the moon, when robotic probes have photographed every planet in our solar system, when we have launched a telescope powerful enough to peer at galaxies forming just 600 million years after the Big Bang, when we have detected gravitational waves from black hole mergers billions of light years away. And yet we cannot come close to reaching our nearest stellar neighbour within a single human lifetime using any propulsion system we have ever tested. The physics of the situation borders on the appearance of absolute prohibition. The chemistry of rockets, the mathematics of orbital mechanics, the sheer emptiness of interstellar space. All of it seems to conspire against the dream of human expansion beyond the solar system. And yet embedded within the same equations that describe the universe's hard limits is something extraordinary. A gift hidden in the mathematics. an answer the universe offers to the very question it appears to forbid. The story of how far humans can really go is not simply a story about how far we fall short, it is a story about the shape of the universe itself. This channel exists to explore exactly these intersections, the places where hard science meets the deepest questions about human possibility, where physics stops being abstract and starts telling you something genuinely staggering about what the cosmos actually permits. If you are the kind of person who looks up at the night sky and wonders, what is out there? Not just aesthetically or philosophically, but in actual scientific terms, then what we do here is built for you. Every video on this channel travels to the same territory, past the comfortable surface of scientific knowledge and into the region where the answers start to get strange, beautiful, and occasionally terrifying. The question we are examining today might be the most important question humanity will ever have to answer in practice, because the answer determines whether our species has a future extending beyond a single fragile planet, orbiting an ordinary star in a universe that, by all current estimates, is approximately 13.8 billion years old and nowhere near finished with the extraordinary things it is capable of producing. If the intersection of hard physics and the deepest questions about human possibility fascinates you, the place where the universe's actual rules start to matter for our actual future. Do yourself a favour and hit the like button and subscribe. It genuinely helps this channel reach people who care about this kind of material, and we release new deep dives on topics exactly like this one on a regular basis. There will be viewers who find this video confirms everything they always suspected about the fundamental strangeness of the cosmos. There will be viewers who find it challenges assumptions they have held for years about what is and is not possible. Both of those responses are exactly right. Now, get yourself comfortable. Whatever you have going on in the next hour or so, set it aside. What follows is not a surface-level summary of space travel. It is a careful, rigorous, genuinely complete examination of what the physics actually permits, what the engineering might eventually achieve, and what all of it means for the long-term future of a species that has always looked up and wondered. To understand where we might go, you first have to understand how we got to where we are. And to understand that, you need to start not with NASA, not with the space race, but with a half-deaf, self-educated schoolteacher living in a small town in rural Russia in the late 19th century. His name was Konstantin Eduardovich Tsiolkovsky, and he was born in 1857 in the village of Izhevskoye, in the Ryazan region of what was then the Russian Empire. When he was 9 years old, a bout of scarlet fever left him almost entirely deaf, cutting him off from most of the conventional educational pathways available to children of his time and place. Unable to attend normal school, he educated himself entirely from his father's library, reading everything he could find in mathematics, physics, chemistry, and astronomy. By his early 20s, he had independently derived mathematical principles that professional scientists at major universities were only just beginning to formally establish. He was, by almost any measure, one of the most remarkable self-educated scientific minds in the entire history of human inquiry. Tsiolkovsky's obsession was space, not in the vague romantic sense that many people mean when they describe themselves as interested in astronomy, but in the specific technical, mathematical sense of a man who genuinely believed that the future of the human species lay beyond Earth, and who spent his entire adult life trying to work out the physics that would make that future possible. Working from his modest home in the city of Kaluga, using self-built equipment and severely limited resources, he developed the theoretical foundations of rocket propulsion decades before anyone had built a rocket capable of reaching significant altitude. He understood the fundamental problem immediately. In order to move through space, where there is no air, and therefore no medium against which conventional propulsion can push, you must carry your own propellant and eject it backward with sufficient force to push yourself forward. This is the principle of the rocket, simple in concept, ferociously difficult in execution, for reasons that Tsiolkovsky himself was the first to precisely and mathematically quantify. In 2003, the same year the Wright brothers made their first powered flight at Kitty Hawk, Tsiolkovsky published a paper containing what would later be called the Tsiolkovsky rocket equation. It is one of the most important equations in the history of space exploration, and in a certain sense, one of the most discouraging. The equation relates the change in velocity a rocket can achieve to three variables: the exhaust velocity of its propellant, the initial mass of the rocket including all fuel, and the final dry mass of the rocket after all fuel has been burned. What the equation reveals, when you work through its implications carefully, is a relationship that feels almost personally hostile to the ambitions of anyone dreaming about interstellar travel. The relationship between fuel required and final velocity is not linear. It is exponential. Each increment of additional velocity you want to achieve does not require a proportional increment of additional fuel. It requires a multiplicative increase in fuel mass, which itself must be accelerated, requiring yet more fuel in a cascade that rapidly becomes mathematically overwhelming. Here is what the rocket equation means in practice. To accelerate a spacecraft to 10% of the speed of light using the most efficient chemical rocket propellant available, liquid hydrogen and liquid oxygen, with an exhaust velocity of around 4.5 kilometers per second, the fuel-to-payload ratio works out to something not merely impractical, but physically impossible to build. You would need a mass of fuel so enormous relative to the dry mass of the spacecraft that no engineering or material science could construct the vessel required to contain it. And 10% of the speed of light is not interstellar in any practical sense. At that velocity, the journey to Proxima Centauri still takes 42 years. You would need 30, 40 or 50% of the speed of light to make interstellar travel practical within a single human lifetime. The rocket equation makes those velocities with chemical propellant not merely difficult but categorically impossible. Tsiolkovsky's equation, applied to chemical rockets and interstellar ambitions, was not merely a description of a challenge. It was a mathematical verdict, and no one has found a way to appeal it. And yet rockets were built. The 20th century, beginning with Tsiolkovsky's paper and culminating 66 years later in the Apollo program, represents the most compressed acceleration in the history of human transportation technology. In 1903, we were flying fragile wood and canvas biplanes barely clearing treetops. By 1969, humans stood on the surface of the moon. The engineering achievements of those intervening decades, liquid-fueled rockets, gyroscopic guidance systems, mastery of orbital mechanics, life support capable of sustaining humans in the vacuum of space, represent a civilizational achievement of extraordinary magnitude. Every step of this progress rested directly on the mathematical foundations Tsiolkovsky had laid from his small apartment in Kaluga, working in isolation decades before anyone took his ideas seriously. The Saturn V rocket that carried Apollo astronauts to the moon remains among the most powerful operational rockets ever built. Its 5 F1 engines produced 1.5 million pounds of thrust each, burning liquid oxygen and refined kerosene, consuming approximately 15 tons of propellant per second at liftoff. It was the culmination of a 60-year arc from theory to hardware, staggering in its engineering sophistication, a monument to what focused civilizational investment can accomplish. And it was completely inadequate for interstellar travel, for precisely the reason Tsiolkovsky had quantified 6 decades before the first one flew. Chemical propulsion had reached its ceiling. The rocket equation was not a starting point anymore. It was a wall. The Apollo program demonstrated conclusively what chemical rockets can and cannot do. They can lift humans off Earth's surface, accelerate them to approximately 25,000 miles per hour, Earth's escape velocity, and carry them on a 3-day journey to the moon. The maximum speed achieved by Apollo 10 during its return to Earth was approximately 24,791 miles per hour, still the record for the fastest any human beings have ever travelled. Against the scale of interstellar space, this velocity is so insufficient as to be almost irrelevant to the conversation. Proxima Centauri at 24,000 miles per hour would take approximately 114,000 years to reach. The Moon is 3 light seconds away. The nearest star is 4 light years away. The difference in scale is not merely quantitative, it is qualitative, a different category of distance entirely. More instructive than what Apollo achieved is what came after it, because the post-Apollo era produced increasingly sophisticated attempts to push robotic spacecraft deeper into the solar system, and those attempts began to reveal the true dimensions of the engineering problem. Gravity assist maneuvers, pioneered through the Mariner and Voyager programs, allowed spacecraft to gain velocity by flying close to planets and borrowing momentum from their orbital motion. Elegant, precise, and entirely dependent on favourable planetary alignment, making the technique essentially useless for targeting distant stars. The Voyager program represents the high water mark of the gravity assist era. Launched in 1977, Voyager 1 and Voyager 2 used Jupiter and Saturn, and in Voyager 2's case Uranus and Neptune, as gravitational slingshots, gaining speed with each flyby, and eventually reaching velocities no rocket burn alone could have achieved. Voyager 1 reached approximately 38,000 miles per hour relative to the Sun. These were astonishing velocities by historical standards, achieved through extraordinarily precise navigation and a once-in-175 years planetary alignment. The favourable alignment of the outer planets that made the Voyager Grand Tour possible occurs only once every 175 years. And even these gravity-boosted speeds, the fastest unassisted human-made objects to ever leave the solar system, translate to journey times of over 70,000 years to the nearest star. Gravity assists are genuine and valuable engineering tools. They are not an answer to the interstellar problem. They are a particularly elegant illustration of just how vast the gap remains between our greatest achievement and what interstellar travel would actually require. Ion propulsion offered another partial answer. Unlike chemical rockets, which burn propellant in a brief and violent combustion, ion engines work by electrically charging atoms of propellant, typically xenon gas, and accelerating them backward using electric fields, generating continuous, gentle thrust that can be maintained for months or years rather than seconds. The exhaust velocity of an ion engine is dramatically higher than any chemical rocket, 10 to 80 kilometers per second compared to 4 or 5, meaning far less propellant is consumed for a given velocity change. NASA's Dawn spacecraft, which visited both the asteroid Vesta and the dwarf planet Ceres in the asteroid belt, used ion propulsion to accomplish trajectories impossible with chemical systems. Japan's Hayabusa missions to asteroids leverage the same technology, but even ion engines, run continuously for years, cannot approach the velocities required for interstellar travel within any reasonable human time frame. They improve on chemical rockets significantly. They improve on the interstellar velocity problem by a fraction of what is actually needed. The gap they close is real. The gap that remains is still orders of magnitude beyond any ion engine ever built or seriously proposed. The honest inventory of where humanity actually stands in terms of propulsion capability, surveyed at the beginning of the 21st century, looks like this. We can reach the Moon in 3 days. We can reach Mars to optimal orbital alignment in roughly 7 months. We can cross the outer solar system in years to decades, depending on the mission profile. We have barely entered interstellar space, the region beyond the Sun's magnetic influence, with Voyager 1 after a journey of nearly 50 years. And even that remarkable achievement has placed a small metal object at a location representing less than 0.2% of the distance to the nearest star. Every propulsion system we have actually built and tested is insufficient for interstellar travel by multiple orders of magnitude. The gap between what we have and what interstellar travel requires is not a gap that can be closed by incremental improvement of existing technology. It requires something qualitatively and fundamentally different. A different energy source, a different propulsion mechanism, a different relationship between fuel mass and achievable velocity, which is precisely where the story stops being about engineering and becomes about physics. So what might that fundamentally different thing be? This is where the story becomes a story about physics rather than engineering, because physics, it turns out, contains something that pure engineering alone could never have provided. It contains a mechanism that does not merely slightly improve the situation, it reframes the entire problem, revealing that what looks like an absolute prohibition on interstellar travel is actually something more nuanced, and in the right circumstances, something extraordinary. The universe appears to be locked. The universe is actually not locked. It has a door in it, and the key to that door is written in equations that were published in a single extraordinary year by a single extraordinary mind. To find this mechanism, you need to go back not to a laboratory, not to a university, not to a space program. You need to go to a patent office in Bern, Switzerland in the year 1905, where a 26-year-old man working as a technical expert on examining other people's patent applications for a modest salary was spending his off hours thinking about the nature of light, time, and the fundamental structure of the cosmos. His name was Albert Einstein, and what he was about to publish would permanently transform the answer to every question about how far any intelligence originating on Earth could ever go. Albert Einstein in 1905 was not yet the cultural icon he would become. He had completed his doctorate but struggled to secure a university appointment. The patent office job was a compromise, a way to pay his bills while he continued to think. What he was thinking about was a problem that had been nagging at the edges of physics for decades: the behavior of light. Maxwell's equations, the foundational laws of electromagnetism developed by James Clerk Maxwell in the 1860s, predicted that electromagnetic waves travel at a specific fixed velocity, approximately 299,792 kilometers per second, or about 186,000 miles per second. But fixed relative to what? In Newtonian physics, velocities are always relative to some reference frame. If you run towards a light source, shouldn't the light appear to move faster relative to you? Careful experiments, including the famous Michelson-Morley experiment, said no. The speed of light appeared identical for all observers regardless of their motion. This made no sense in classical physics. It made perfect sense once Einstein showed why. Einstein's special theory of relativity, published in June 1905, rested on two postulates. The first was the principle of relativity. The laws of physics are identical in all inertial reference frames. No experiment you can conduct inside a sealed box moving at constant velocity can determine whether you are moving or at rest. The second postulate was more radical. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. These two postulates sound modest. Their mathematical consequences are anything but. If the speed of light is fixed for all observers, and if the laws of physics are the same for all observers, then something else must yield to accommodate this requirement. What Einstein demonstrated with complete mathematical precision is that what yields is time itself. Time is not universal. Time is not a fixed background against which events occur identically for every observer. Time is flexible, observer-dependent, and measurable at genuinely different rates by observers in different states of motion. This discovery is, for interstellar travel, the most important thing physics has ever produced. Every calculation about how far a human being could travel in a single lifetime traces directly back to this single insight, worked out by a 26-year-old in a Swiss patent office in the summer of 1905. The phenomenon Einstein's equations describe is called time dilation. It is not a statement about clocks being unreliable, or instruments malfunctioning, or human perception distorting reality. It is a statement about the structure of reality itself. Time actually passes at different rates for observers moving at different velocities relative to each other. The faster you move, the more slowly time passes for you relative to a stationary observer. At the low velocities experienced by everything humans have ever built, this effect exists, but is vanishingly small. GPS satellites, moving at about 8,800 miles per hour, experience measurable time dilation. Their onboard clocks must be corrected to maintain GPS accuracy, which they are, with extraordinary precision, confirming the effect through practical engineering rather than just laboratory experiment. But the dilation at those speeds is tiny. The effect only becomes genuinely dramatic, becomes the gift hidden in the physics, as you approach a significant fraction of the speed of light. And that is precisely where the story of interstellar travel becomes, against all apparent expectations, not hopeless but genuinely remarkable. The experimental confirmation of time dilation came not just from theory, but from direct physical observation. Cosmic rays from deep space strike Earth's upper atmosphere and create particles called muons. Muons are unstable. They decay rapidly, with a half-life of approximately 2.2 microseconds. At the speed they travel, around 98% of the speed of light, they should disintegrate within roughly 660 meters of their creation. Yet muons are detected at Earth's surface in large numbers, having survived a journey of approximately 15 kilometers through the atmosphere. The reason is time dilation. Moving at 98% of the speed of light, the muon's internal clock runs so much more slowly relative to Earth's reference frame that, from our perspective, it survives long enough to complete the journey. From the muon's own perspective, the atmosphere is length contracted, so effectively shorter, and the journey takes only the duration its own internal clock measures. Both perspectives are self-consistent. This is not a paradox, it is simply how the universe works, confirmed by millions of muons reaching the ground every single second of every single day. The mathematical tool that captures time dilation precisely is the Lorentz factor, written with the Greek letter gamma. It is the factor by which time slows, and equivalently by which lengths contract in the direction of motion for a moving object relative to a stationary observer. At 10% of the speed of light, gamma is approximately 1.005, almost no time dilation. At 50% of the speed of light, gamma is approximately 1.15, still modest. At 80% it is 1.67, at 90% it is 2.29, and then the curve steepens dramatically. At 99% of the speed of light, gamma is approximately 7.09. At 99.9% it is 22.4, at 99.99% it is 70.7. As velocity approaches at the speed of light asymptotically, gamma approaches infinity, meaning the traveller's experienced time approaches zero, while the universe's clocks run normally outside. This is not a theoretical extrapolation. This is what the mathematics says, confirmed by every experimental test ever conducted. This is the loophole the universe contains. This is the door hidden in the wall. The wall that says you cannot travel faster than light also contains, written within its own equations, the gift that makes the wall navigable, the compression of personal time that grows without bound as you approach the limit. The universe does not forbid interstellar travel for the traveller. It forbids it for the universe watching from the outside. Now apply these numbers to real destinations. Proxima Centauri is 4.24 light years away. If a spacecraft could be accelerated to 99% of the speed of light, with a Lorentz factor of approximately 7, the journey would take 4.24 years as measured from Earth's surface. but the crew aboard would experience only about 7 months. 7 months to travel to another star system. From the crew's perspective, the journey to our nearest stellar neighbour, the journey that at Parker Solar Probe speed takes 6,400 years, takes less time than a human pregnancy. The destination is unchanged. The distance from Earth's perspective is unchanged. But the traveller's experience time is compressed by the Lorentz factor, making a journey that appears interminable from the outside appear entirely manageable from the inside. This is not a trick and not a metaphor. This is what the equations of physics actually say about how the universe works. The cosmos contains, within its fundamental architecture, a mechanism that makes interstellar travel genuinely possible. Not easy, not soon, but possible for the people making the crossing. At 99.9% of the speed of light, with a Lorentz factor of 22, the implications expand dramatically. Sirius, the brightest star in Earth's night sky, 8.6 light-years distant, would be reached in roughly 5 months of crew experience time. The Pleiades star cluster, 444 light-years away, visible to the naked eye as a tight grouping of blue-white stars in the constellation Taurus, would be reached in a crew experience journey of approximately 20 years. Consider what that means. 444 light-years is an almost incomprehensible distance by any Earth-based standard. Light itself takes 4.5 centuries to make the crossing. A spacecraft travelling at 99.9% of the speed of light takes 444 years in Earth time as well, but the crew age is only 20 years. A person who left Earth at 30 years of age would arrive at the Pleiades at 50, having experienced a reasonable working lifetime of travel. The Pleiades are over 400 light-years away, and yet in terms of the traveller's actual biological experience, they are not unreachable at all. At 99.99% of the speed of light, with a Lorentz factor of approximately 70, the accessible territory expands to proportions genuinely difficult to absorb. The Orion Nebula, 1,344 light-years from Earth, a stellar nursery visible to the naked eye as a fuzzy patch below Orion's belt, would be reached in about 19 years of crew time. The centre of our Milky Way galaxy, 26,000 light-years away, could be reached in approximately 11 years as experienced by the crew. The Andromeda Galaxy, our nearest major galactic neighbour at 2.5 million light-years, could be crossed in roughly 36 years of crew experience time. 36 years, 2.5 million light-years. By any human measure, that is a finite, surveyable span of experience. A person could leave Earth at age 25 and arrive at Andromeda at 61, having lived a single continuous human lifetime of travel. The universe at sufficiently high fractions of the speed of light begins to look, in terms of personal experience, almost navigable. The twin paradox makes time dilation's human implications most vivid. Imagine two twins. One remains on Earth, the other boards a spacecraft travelling to Proxima Centauri at 99% of the speed of light. The traveller completes the round trip, out to Proxima and back. From Earth's perspective, the journey takes approximately 8.5 years. The travelling twin, with time compressed by a Lorentz factor of 7, ages about 14 months during the entire round trip. They return to find their sibling nearly 9 years older, while they themselves have aged just over a year. This asymmetry is not a paradox in the logical sense. It contains no contradiction. It is fully explained by the fact that the travelling twin underwent acceleration and deceleration, breaking the symmetry between the two reference frames. Both twins can compare their ages afterward. Both measurements will be correct. The difference in their ages is real, permanent, and entirely consistent with every verified principle of special relativity. The universe does not treat all observers identically across all conditions. It treats them consistently, and consistency at relativistic velocities produces effects that feel impossible until you've absorbed the mathematics thoroughly. Alongside time dilation operates a companion effect called length contraction. Just as time slows for a moving observer relative to a stationary one, distances contract in the direction of motion from the moving observer's perspective. A traveller moving at 99% of the speed of light does not experience the distance to Proxima Centauri as 4.24 light years. They experience it as approximately 0.6 light years, contracted by the Lorentz factor of 7. This is why the journey subjectively takes only 7 months, rather than 4.24 years. Both the time compression and the length contraction are fully consistent with each other, and with the requirement the speed of light remain constant for all observers, the universe accommodates the fixed speed of light by making time and space themselves flexible. The traveller moves through genuinely contracted space in genuinely compressed time. There is no trick and no approximation. The universe offers a genuinely different geometry of space-time that becomes accessible as velocities approach the speed of light, and that geometry contains within it the real possibility of crossing distances that would otherwise require geological timeframes. But here is where the gift begins to reveal its cost. Time dilation is real and physics confirmed, genuinely compressing the traveller's experience of an interstellar journey. But achieving the velocities at which these effects become useful requires energy, and the energy required grows not linearly but asymptotically as you approach the speed of light. In Newtonian mechanics, kinetic energy is 1/2 times mass times velocity squared. Double velocity, quadruple kinetic energy. In relativistic mechanics, the relationship between energy and velocity is governed by the Lorentz factor, and as velocity approaches light speed, the required kinetic energy approaches infinity. There is no finite quantity of energy that can accelerate any object with rest mass to exactly the speed of light. You can approach it asymptotically, 99%, 99.9%, 99.99%. Each additional fraction of a percent costs exponentially more energy than the fraction before it, in a curve that steepens without limit. The gift the universe offers through time dilation comes with a price tag, written in units of energy, and the price tag does not offer discounts. The universe is generous, it allows the crossing. The universe is also honest. It requires payment in a currency that does not yet exist at the scale required. To put real numbers on this energy problem, accelerating a single kilogram of payload to 90% of the speed of light requires approximately 43 petajoules of kinetic energy. A petajoule is 1 quadrillion joules. Total global energy production of human civilization from all sources in a year is approximately 600 exajoules or 600,000 petajoules. Accelerating 1 kilogram to 90% of light speed requires energy equal to roughly 7,000ths of 1% of annual global energy production. That sounds almost manageable, until you realize that an actual crewed spacecraft would mass not 1 kilogram but tens or hundreds of thousands of tons, including life support, hull structure, crew quarters, radiation shielding instruments, food, water, and propellant for deceleration at the destination. The energy required to accelerate such a vessel to a significant fraction of the speed of light is not merely large, it is, by any current measure of human energy production, incomprehensible, many orders of magnitude beyond everything our civilization currently generates from all sources combined, with no conversion efficiency losses assumed away. There is an additional complication that simple time dilation calculations often gloss over: deceleration. Time dilation tells you how long the journey takes from the crew's perspective. But arriving at Proxima Centauri at 99% of the speed of light is not an arrival in any useful sense. You streak through the system in hours and continue into empty space forever. You need to slow down, to shed velocity from near light speed to something compatible with orbital insertion or systematic exploration. Deceleration requires just as much energy as acceleration, applied in the opposite direction. If you plan to return to Earth, you need to accelerate again and then decelerate again. Every leg of the journey carries its own full energy bill. The round-trip energy requirements for a crewed interstellar mission with full deceleration at each end are not merely doubled, but multiplied in ways that make already enormous numbers considerably worse, depending on the mission profile and the propulsion system's efficiency. Physics gives us the gift of time dilation and simultaneously presents the bill, written in units of energy that dwarf everything human civilization has ever produced or stored. One elegant approach to the propellant problem is continuous acceleration. Rather than a massive burn to reach target velocity followed by coasting, imagine a spacecraft maintaining constant acceleration at exactly 1g, standard Earth gravity, for the entire first half of the trip, then decelerating at 1g for the second half to arrive essentially at rest. A continuous 1g profile is appealing for multiple reasons. It provides natural artificial gravity throughout the journey, eliminating the serious physiological problems associated with extended weightlessness, bone density loss, cardiovascular deconditioning, fluid shifts. It carries the spacecraft into deeply relativistic velocities through gradual, continuous acceleration rather than a single extreme burn. At 1g of constant acceleration, a spacecraft reaches 50% of the speed of light in roughly 11 months, 90% within approximately 2 years, and 99% within approximately 6 years. The asymptote prevents reaching exactly 100%, but 99% provides a Lorentz factor of 7, and that is sufficient to make interstellar distances genuinely manageable from the crew's lived experience. Under a 1g continuous acceleration and deceleration profile, the destinations accessible within a single crew lifetime expand to extraordinary range. A round trip to Proxima Centauri takes approximately 3.5 years of crew experience time. A round trip to Sirius takes about 7 years. A one-way journey to the galactic center, 26,000 light-years, takes approximately 21 years of subjective crew time. A one-way journey to the Andromeda Galaxy, 2.5 million light-years, takes approximately 29 years of subjective crew time, 29 years to reach another galaxy. These numbers are the direct mathematical output of the Lorentz factor, of velocities achieved by continuous 1g acceleration, fully consistent with special relativity as tested in particle accelerators and GPS satellites and cosmic ray experiments every day. The universe under these conditions begins to look almost navigable, at least for the traveller. The phrase that always follows is the phrase that matters most. A spacecraft capable of maintaining continuous 1g thrust for decades requires a power source and propulsion system so far beyond anything humans have ever built that the engineering gap between here and there is one of the greatest challenges our species has ever conceptualized. This is where the conversation leaves pure physics and enters engineering, where the question shifts from whether the universe permits interstellar travel to whether we can build the machine that does it. And this is where the answer begins to look less like never and more like not yet. But here are the paths. The engineering approaches that have been seriously proposed and studied fall into several broad categories, each representing a genuine attempt to close the gap between our current velocity ceiling and what interstellar travel requires. None of them are ready. Several are not obviously impossible. One or two of them, given sufficient time and sustained investment, might actually work. That is a different statement about the future of human spaceflight than anything the rocket equation alone would suggest. The history of these proposals is, in its own right, a remarkable story of scientific ambition, technical creativity, and the sustained willingness to take seriously problems that most people assume are permanently beyond reach. The first serious engineering proposal for interstellar travel that moved beyond pure chemical rocketry came in the late 1950s, and it was as audacious as anything ever seriously advanced by credentialed physicists. Project Orion was the brainchild of physicist Theodore Taylor and mathematician Freeman Dyson, working under DARPA at the General Atomics Research Facility in California. The basic concept was startling in its directness. Propel a spacecraft by detonating nuclear bombs behind it. A massive steel pusher plate at the rear of the spacecraft would absorb the energy of each nuclear detonation, and the expanding plasma would push the plate and the spacecraft forward. Each detonation would produce a pulse of acceleration. Detonate enough bombs in rapid succession and you could maintain effectively continuous thrust. The concept sounds absurd at first contact. The physics, as Dyson and Taylor worked through it exhaustively, was entirely sound. Nuclear pulse propulsion, executed correctly, could achieve specific impulse values many times superior to any chemical rocket system, meaning dramatically more velocity per unit of propellant mass, exactly the improvement the Col-Koffsky equation requires. The team built scale models, ran calculations, and found no fundamental physical obstacle. The pusher plate concept was tested with non-nuclear explosives and worked as designed. Orion was not a thought experiment. It was an engineering program with real hardware, run by real physicists, that produced real results. Results suggesting interstellar travel was not centuries away, but potentially within reach of the mid-20th century technology, given only the will to pursue it. The numbers that Project Orion's team calculated were genuinely impressive. Using nuclear devices available in the late 1950s, the team estimated that an Orion vehicle could achieve velocities on the order of 3 to 8% of the speed of light. At 5% of light speed, the journey to Proxima Centauri would take approximately 85 years, longer than a single human lifetime, but manageable for a multi-generational crew or with significant life extension technology. At 8%, the crossing takes approximately 50 years, within a single lifetime for a crew member who departed in their 20s. Freeman Dyson worked out a concept for a massive Orion vessel, a city-scale spacecraft carrying hundreds or thousands of people, capable of reaching Alpha Centauri within a human generation. This was a detailed engineering proposal worked out by some of the most capable physicists of the mid-20th century, using technology that actually existed at the time. Not technology extrapolated into the future, but technology already built and tested. Dyson believed, and said publicly on multiple occasions, that Project Orion represented a genuine and practical path to interstellar travel. Then it was cancelled, not because the physics was wrong, but because of geopolitics. The Partial Nuclear Test Ban Treaty of 1963, negotiated primarily to reduce radioactive fallout from atmospheric weapons testing, prohibited the detonation of nuclear devices in the atmosphere, in space, and underwater. Project Orion required detonating nuclear devices in space. The treaty did not specifically target Orion, it targeted weapons tests, but it effectively made the project legally impossible to continue under United States law. Funding was cut, the team dispersed. Freeman Dyson spent the rest of his long and distinguished career occasionally reflecting on what the trajectory of human spaceflight might have looked like had Orion been allowed to continue. He believed, with some empirical justification, that nuclear pulse propulsion represented a genuine and practical route to interstellar capability, a route foreclosed not by any physics or engineering obstacle, but by geopolitics and a failure of civilizational imagination. The equipment built and tested during Orion's brief operational life, including non-nuclear scale models confirming the pusher plate concept worked as designed, sits in archives. The concept was never invalidated by experiment. It was simply stopped, and the question of what practical interstellar propulsion might look like was handed forward to subsequent generations to answer. That subsequent generation produced Project Daedalus, the most detailed engineering study of an interstellar spacecraft ever completed. Conducted by the British Interplanetary Society between 1973 and 1978, Daedalus assembled a team of engineers and physicists and asked them to design, as rigorously as available knowledge permitted, an uncrewed robotic probe capable of reaching Barnard's star, a red dwarf approximately 6 light-years from Earth, within a human lifetime of mission duration. The propulsion concept selected was inertial confinement fusion, small pellets of deuterium-helium-3 fuel compressed and ignited by electron beams at a rate of approximately 250 pellets per second, producing a continuous high-velocity plasma exhaust. The study ran for 5 years and produced a specific detailed design, a 2-stage vehicle approximately 190 meters long, massing approximately 54,000 tons total, of which roughly 50,000 tons was propellant. The Daedalus vehicle would accelerate continuously for approximately 4 years, reach a maximum velocity of 12.2% of the speed of light, then coast for the remaining 46 years of a 50-year mission to Barnard's star, 12.2% of the speed of light. That is 36,400 kilometers per second, not a round number, not an approximation, but a specific engineering output from a specific 5-year design study by serious scientists who did the math. Project Daedalus's design was meticulous and serious, and sobering in what it revealed about the true engineering scale of interstellar travel. The most striking figures were the fuel requirements. 50,000 tons of propellant, including helium-3, a rare isotope essentially absent from Earth's surface in usable quantities, would need to be mined from the upper atmosphere of Jupiter using mining facilities that did not exist and would require their own extraordinary engineering program to build and operate. The Daedalus team acknowledged this openly. The mission assumed a level of industrial development in the outer solar system that was, from the vantage point of the 1970s, at minimum several decades in the future. The study was not claiming Daedalus could be launched soon. It was making the more fundamental claim that the physics and engineering of interstellar travel, while demanding, were not obviously impossible, that given sufficient development of solar system infrastructure, an uncrewed probe to a nearby star was a legitimate engineering objective. The report concluded that humanity could build such a vessel within a century. Given the necessary industrial foundation and the political and cultural will to commit to the project, the most important limitation Daedalus acknowledged openly was its complete absence of deceleration capability. At 12.2% of the speed of light, the Barnard star encounter would be a flyby. The probe would pass through the system in hours, deploying sub-probes and cameras as it did, before continuing outward into interstellar space permanently. This was a deliberate concession to the propellant problem. Adding deceleration would have multiplied fuel requirements far beyond what even Jupiter atmosphere mining could feasibly supply. Subsequent studies, including the later Project Icarus, which revisited Daedalus with updated physics and material science, attempted to incorporate deceleration into the mission architecture, but every approach that included stopping at the destination dramatically increased mission complexity and total vehicle mass. The deceleration problem is not a minor footnote in interstellar engineering. It is a central and deeply challenging obstacle, requiring either a propulsion system of extraordinary mass ratio or a way to decelerate that does not depend entirely on carried propellant. Its solution is not yet in sight, and no one has proposed an approach that the majority of working engineers consider clearly workable at the required scale. In 2016, a radically different approach arrived when Yuri Milner announced the Breakthrough Starshot initiative, backed by Stephen Hawking, Mark Zuckerberg and others. Breakthrough Starshot abandoned the idea of sending a massive crewed ship or even a substantial robotic probe. Instead, it proposed sending thousands of gram-scale light sails, spacecraft the mass of a postage stamp, carrying miniaturized instruments, propelled not by any onboard propellant, but by a ground-based laser array of roughly 100 gigawatts. The laser would shine on a sail of ultra-reflective material only a few hundred atoms thick over approximately 10 minutes, accelerating it to roughly 20% of the speed of light. At that velocity, the journey to Alpha Centauri takes about 22 years. The miniaturized instruments would photograph the Alpha Centauri system during a high-speed flyby, then transmit images back to Earth, a transmission taking 4 years to arrive at the speed of light. The scientific return would be limited by the gram scale of the payload, but the principle, actually sending something built by humans to another star within a human lifetime, would be historically unprecedented, and that principle matters enormously. The breakthrough. Starshot proposal was taken seriously by the physics community. Laser propulsion and light sails are both physically reasonable concepts with experimental backing. The engineering challenges are formidable, but not obviously impossible in principle. The laser array would need to be positioned at high altitude or in space to minimize atmospheric distortion. The sail material would need extremely precise engineering to survive near-instantaneous high-G acceleration. The miniaturized electronics would need to withstand decades of intense radiation and interstellar dust impacts. None of these are physics problems, they are engineering problems, the kind that can in principle be solved given sufficient investment and ingenuity. The major limitation Starshot shares with Daedalus is that it is not a human mission. At gram scale, the spacecraft carries no crew and no capacity beyond photographing its destination and transmitting data home. It is a probe, not a vessel. It is the first serious step in the direction of the stars, and not the crossing itself. But every journey begins with a first step, and Breakthrough Starshot would be the first one that actually crossed interstellar distance within a human lifetime. Antimatter. Propulsion represents the theoretical upper bound of what known physics could offer as an energy source. When matter and antimatter meet, they annihilate completely, converting 100% of combined mass into energy in the form of gamma rays and high-energy particles. This is the most energy-dense process the universe permits, not 10 or 20 or even 60% mass-energy conversion, but 100%. Compare this to chemical combustion, which converts about 1/10 billionth of its mass to energy, to nuclear fission, which converts roughly 1/10 of 1%, to nuclear fusion, which converts approximately 1%. Antimatter annihilation converts all of it. A single kilogram of antimatter, combined with a kilogram of matter, would release approximately 90 petajoules of energy, equivalent to roughly 21 megatons of TNT. If the annihilation products could be directed efficiently as exhaust, the specific impulse of an antimatter rocket would be sufficient to accelerate a spacecraft to a significant fraction of the speed of light. The physics is not in question. The concept is not speculative. The production problem, however, is catastrophic in a way that makes every other interstellar propulsion challenge look modest by comparison. Antimatter does not exist in usable quantities anywhere accessible to humanity. It must be manufactured, created in particle accelerators by colliding high-energy particles and capturing the antimatter that results. The world's most powerful particle physics facility, CERN, produces antimatter as a byproduct of its experiments. Across all particle accelerators on Earth combined, total global annual production of antimatter, primarily positrons and antiprotons, is approximately 10 to 15 nanograms per year. A nanogram is 1 billionth of a gram. 10 nanograms is a quantity so small that it would be invisible to the naked eye and detectable only with highly sensitive instrumentation. The energy cost of producing that antimatter vastly exceeds the energy it could release. The production process loses efficiency by factors of billions relative to the energy stored. To fuel even a modest antimatter-propelled spacecraft would require kilograms or tons of antimatter. At current global production rates, accumulating that quantity would take not centuries but effectively geological timeframes. antimatter propulsion is the most energy-efficient propulsion mechanism physics permits, and the most practically inaccessible at any foreseeable level of human industrial development. Fusion propulsion occupies the promising middle ground between the practicality of nuclear fission and the theoretical perfection of antimatter. Nuclear fusion, the process that powers the sun, fusing light atomic nuclei together to release energy, offers energy density many times greater than fission and produces far less long-lived radioactive waste. The fuel for fusion, isotopes of hydrogen, particularly deuterium and helium-3, is abundant in the outer solar system in quantities that dwarf any terrestrial fuel resource. The main obstacle to fusion propulsion for the better part of 7 decades was that no one had demonstrated sustained net fusion energy gain in a controlled laboratory setting. That changed on December 5, 2022, when researchers at the National Ignition Facility at Lawrence Livermore National Laboratory in California achieved ignition, a fusion implosion that released more energy from the fusion reaction than the laser energy delivered to trigger it. It was a landmark moment in energy physics, the first confirmed demonstration that net fusion energy production in a controlled laboratory setting is achievable. It was also explicitly the first experimental step toward the class of propulsion systems that serious interstellar missions would require. The physics is confirmed, the engineering from laboratory demonstration to spacecraft propulsion is the work of decades, but the path is now no longer theoretical. It begins from a confirmed experimental result. The National Ignition Facility's December 2022 result was technically specific in its demonstration and modest in its scale. The fusion yield was approximately 3.15 megajoules compared to 2.05 megajoules of laser input, a gain factor of about 1.5. This is nowhere near sufficient to run a power plant or a spacecraft, but it proved the physical principle under real experimental conditions. The engineering roadmap from laboratory ignition to practical fusion propulsion runs through a series of scaling challenges, demonstrating progressively higher gain factors, developing materials capable of withstanding the plasma environment over operational lifetimes, solving the engineering of continuous or pulsed fusion operations in a spacecraft-compatible configuration, and ultimately integrating all of this into a propulsion system that can be built, maintained and operated in deep space over years or decades. None of these steps are trivial. In the judgment of most physicists and engineers working in the field, all of them are physically achievable on a timescale of decades to a century. The question is not whether fusion propulsion is physically possible. The physics says yes. The question is how fast the engineering can advance, and that depends on choices as much as on science. The Bussard interstellar ramjet, proposed by physicist Robert W. Bussard in 1960, attempted to sidestep the propellant problem entirely by drawing fuel from the interstellar medium. Rather than carrying all propellant, a ramjet would scoop up the sparse hydrogen naturally present throughout interstellar space, compress and fuse it, and use the resulting energy for thrust. Interstellar space is not completely empty. It contains approximately 1 hydrogen atom per cubic centimetre on average. A sufficiently large magnetic scoop, Bussard argued, could collect enough hydrogen at relativistic speeds to sustain a fusion drive, giving the spacecraft an effectively unlimited propellant supply mined from the fuel and space it passes through. The concept appeared in science fiction extensively throughout the 1970s. However, detailed subsequent analysis revealed serious physical obstacles. The interstellar medium is sparser in many regions than Bussard's original estimates assumed. The drag created by the magnetic scoop may exceed the thrust it enables at practical hydrogen densities, and the specific proton-proton fusion reaction required with low-density interstellar hydrogen is among the most difficult to ignite and sustain. The ramjet remains a beautiful idea that the physics has not fully cooperated with. Solar sails require no onboard propellant at all, using instead the pressure of photons from either sunlight or a powerful laser array to push a reflective surface and accelerate the spacecraft. The concept has been experimentally demonstrated. Japan's IKAROS mission successfully deployed and operated a solar sail in 2010, and the Planetary Society's Light Sail 2 demonstrated controlled solar sail maneuvering in 20s. The physics is confirmed and the concept is real. For interstellar travel, the problem is twofold. Sunlight pressure falls off with the square of distance, so beyond the inner solar system, natural solar acceleration becomes negligible, and the sail must be enormously large relative to the payload mass to develop useful thrust at any distance. Laser propulsion addresses the first problem by substituting a focused laser beam for diffuse sunlight, which is the basis of breakthrough starshot. But a laser array powerful enough to accelerate a human-scale spacecraft to a meaningful fraction of light speed would need to be so large and energy-intensive that it represents an engineering project dwarfing anything currently in existence by many orders of magnitude. The principle is experimentally confirmed. The implementation at human mission scale lies far beyond current capability. With all these propulsion concepts surveyed, the honest gap picture is this. At one end stand our fastest actual spacecraft, Voyager 1 and New Horizons, at roughly 35 to 40,000 miles per hour, a tiny fraction of 1% of the speed of light. At the other end is the threshold at which interstellar travel becomes practically achievable within a human lifetime, roughly 10 to 20% of light speed, depending on destination and mission architecture. Between these 2 points lies a gap of approximately 2 to 3 orders of magnitude. This is not an incremental gap closable by building slightly better rockets. It requires a qualitative shift in propulsion technology, from chemical combustion to nuclear fission to fusion to something capable of achieving a substantial fraction of light speed over sustained periods. The leading candidates, fusion propulsion, laser propulsion, and possibly technologies not yet conceived, are all physically real and permitted by the laws of nature. They are simply not ready, and the timeline for their development is measured in decades and centuries, not years. The gap is real, its closure is not guaranteed, but it is a gap in engineering, not a prohibition in physics. The nearest star system to our own is the Alpha Centauri system, a triple-star arrangement of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are a binary pair, orbiting each other at distances comparable to the separation between our Sun and Saturn over a period of approximately 80 years. Alpha Centauri A is slightly larger and more luminous than our Sun. Alpha Centauri B is slightly smaller and dimmer. Proxima Centauri is a red dwarf, far smaller, cooler and dimmer, orbiting the binary pair at an enormous distance, requiring approximately 550,000 years to complete one orbit. Proxima is the actual nearest individual star to Earth, fractionally closer than A and B. The Alpha Centauri system is the only other star system currently accessible to even theoretically plausible near-future propulsion architectures. If humanity sends its first probe or crewed mission to another star system, the most likely destination, for reasons of pure proximity and available observational knowledge, is somewhere in the Alpha Centauri neighborhood. And that neighborhood contains a planet that makes the target more than merely geographically convenient. In 2016, astronomers announced the discovery of Proxima Centauri B, a planet orbiting Proxima Centauri with a mass at least 1.3 times that of Earth, completing one orbit every 11.2 Earth days, at a distance placing it within the habitable zone, the range of orbital distances where liquid water could theoretically exist on the surface under suitable atmospheric conditions. This discovery transformed the Alpha Centauri system from merely the nearest stellar neighborhood to potentially the nearest neighborhood, containing a world where life might exist. The announcement generated both tremendous excitement and appropriate scientific caution. Proxima B's existence is confirmed through multiple observational methods. Its surface conditions remain deeply uncertain. Proxima Centauri is a flare star. It regularly emits X-ray and ultraviolet flares many times more energetic than the most powerful solar flares our Sun produces. Whether Proxima B's atmosphere could survive such bombardment over billions of years, or whether it retains any atmosphere at all, is a question current telescope technology cannot definitively answer. But the planet exists. The orbit is real. The physical possibility of habitability is genuine and scientifically worth taking seriously. The habitable zone question around Proxima Centauri is complicated by tidal locking because Proxima b orbits so close to its dim star, closer than Mercury orbits our Sun, which is necessary for a cool red dwarf's habitable zone. The gravitational interaction between planet and star over billions of years almost certainly results in tidal synchronization. One hemisphere permanently faces the star in constant illumination, while the other faces permanently away in perpetual darkness and extreme cold. Life as we know it on Earth evolved under day-night cycling, seasonal variation, and moderate temperature distribution. A tidally locked planet presents a radically different environment. A scorched dayside, a frozen nightside, and a potentially temperate terminator band between them, where temperatures might permit liquid water. Atmospheric circulation models suggest that a sufficiently thick atmosphere could redistribute heat and maintain survivable conditions over wider regions. Whether Proxima b retains such an atmosphere, given the star's intense early flaring activity, remains one of the central open questions in contemporary exoplanet science. The planet is there. The conditions are uncertain. That uncertainty is itself a reason to go. 40 light-years from Earth lies a system that has become one of the most scientifically significant discoveries in the history of the search for habitable worlds. TRAPPIST-1 is an ultra-cool dwarf star hosting 7 confirmed rocky Earth-sized planets. 3 of these, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1ig, orbit simultaneously within the star's habitable zone. The discovery, announced in February 2017, was remarkable for its density of potentially habitable worlds at a single star, and for the fact that all 7 planets are Earth-sized and dense enough to be rocky rather than gaseous. The James Webb Space Telescope has been conducting detailed atmospheric observations of the TRAPPIST-1 worlds since 2022. Early results show that TRAPPIST-1b, the innermost planet, lacks a substantial atmosphere, consistent with intense stellar radiation at close orbital distance. The habitable zone planets remain under active investigation. TRAPPIST-1 is too distant for any near-future propulsion system, but its systematic characterization from Earth is accelerating rapidly, and may provide the first genuine evidence of biosignature chemistry beyond our solar system. The stellar neighbourhood within roughly 20 light-years of Earth contains approximately 60 known star systems, comprising around 85 individual stars of various types. The great majority are red dwarfs, small, dim, extraordinarily long-lived stars that are the most common stellar type in the galaxy, but that present both tidal locking and flare challenges. Several systems within this neighbourhood warrant particular scientific attention. Epsilon Arid Ni at 10.5 light-years, a young sun-like star with at least one confirmed planet, and a prominent debris disk resembling our early solar system. Tau Ceti at 11.9 light-years, a sun-like star with several candidate planets including at least one potentially into the habitable zone. 61 Cygni at 11.4 light-years, binary pair of K-type orange stars long studied as candidates for hosting planetary companions. Each of these systems is thousands of years away at current propulsion levels. At the velocities that serious propulsion proposals are beginning to describe, several could in principle be reached within a human lifetime. They are not merely abstract data points in a stellar catalogue. They are specific, named, increasingly well-characterized destinations the potential targets of the first interstellar missions our civilization will ever attempt. Beyond the stellar neighborhood lies the Milky Way, our home galaxy, a flattened disk structure approximately 100,000 light-years in diameter, containing between 200 and 400 billion stars. We are positioned roughly 26,000 light-years from the galactic center, in a region of moderate stellar density within a spiral arm. The galaxy is not structurally uniform. The central bulge is densely packed with ancient stars and permeated with high-energy radiation from stellar interactions and the supermassive black hole at its core. Sagittarius, a star with a mass approximately 4 million times that of our Sun. The outer regions of the disk are far sparser. Under the 1G continuous acceleration profile we calculated earlier, with a sufficiently capable propulsion system, the galactic center could be reached in approximately 21 years of crew experience time, though Earth time would read 26,000 years elapsed. The full diameter of the galaxy could be traversed in a crew experience journey of approximately 50 years, though the Earth that launched the mission would be 100,000 years older by the time of arrival at the far edge. And then there are the galaxies beyond our own. The universe contains an estimated 2 trillion galaxies, a number dramatically revised upward from the previous estimate of 200 billion, based on deep survey data analysed in 2016. The Milky Way belongs to a local group of roughly 50 galaxies, dominated by 2 large spirals, the Milky Way and Andromeda, surrounded by smaller dwarf satellite galaxies. Beyond the local group, clusters and superclusters of galaxies stretch in every direction, separated by vast cosmic voids where the density of matter is extraordinarily low. At the distances of these vast structures, an entirely different phenomenon comes into play, one unrelated to propulsion technology, time dilation, or engineering, but determined entirely by the large-scale behavior of space-time. This phenomenon was discovered in 1998, earned its discoverers the Nobel Prize in Physics in 2011, and sets the only absolute limit on how far any intelligence originating from Earth can ever reach, regardless of technology, regardless of time elapsed, regardless of any other consideration: dark energy. The discovery is one of the most startling events in the history of science. In 1998, 2 independent teams of astronomers, one led by Saul Pearl Mutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe. They expected to find deceleration, the universe still expanding from the Big Bang but gradually slowing under the gravitational attraction of all the matter it contains. What they found was the opposite. The expansion was accelerating. The universe was expanding faster and faster, driven by some form of energy permeating empty space, constituting approximately 68% of the total energy content of the cosmos, yet having no direct effect on local gravitational systems like the solar system or even the galaxy. This energy, called dark energy because its nature remains poorly understood even today, was not predicted by standard cosmological models of the era. Its discovery required rewriting the physics of the universe on its largest scales. Pearl, Mutter, Schmidt and Rees share the 2011 Nobel Prize in Physics for what remains one of the most unexpected experimental results in the history of observational astronomy, a discovery that set the universe's final boundary and in doing so, defined for the first time exactly how much of the cosmos any civilization from Earth could ever hope to reach. The implications of accelerating expansion for how far humanity can go are profound and absolute. Because the expansion of space is accelerating, distant galaxies are not merely moving away from us, they are moving away at increasing speed. Sufficiently distant galaxies are already receding faster than the speed of light. This does not violate special relativity. Special relativity limits the speed of objects through space, not the speed at which space itself expands. The boundary at which recession velocity equals the speed of light is called the Hubble sphere, currently at approximately 14 billion light-years from Earth. Galaxies beyond this boundary are receding from us faster than light right now. We can still detect ancient light from them, emitted long before they cross this threshold, travelling toward us for billions of years. But we cannot send anything to them. Whatever we launch in their direction will never close the gap. Every moment of travel, the destination recedes faster than the traveller advances. There is no propulsion technology, no matter how advanced, that can overcome a recession velocity exceeding light speed driven by the fabric of space expanding. The cosmological event horizon is a related but more final concept, the boundary beyond which no signal or object sent today can ever reach any destination, given literally infinite time. Due to the ever-increasing acceleration of expansion, this horizon sits at approximately 16 to 17 billion light-years from Earth in all directions. Galaxies beyond this boundary are already so far away and receding so rapidly that even light sent towards them today will never arrive. The expanding distance will always exceed the distance that any beam of light can close at every future moment. This is the absolute limit, not a limit set by engineering, not a limit set by available energy, a limit set by the structure of the universe itself, by the dark energy that fills empty space and drives the acceleration of its expansion. Beyond 16 to 17 billion light-years, no object originating from Earth can ever go, regardless of technology, regardless of time. The universe draws a final boundary. Everything outside it is permanently and irrevocably beyond reach. What this means in practice is that the universe accessible to humanity is already being irreversibly reduced. Every year, some galaxies that were previously within the cosmological event horizon cross it and become permanently unreachable. The universe's accelerating expansion is systematically closing doors. At the moment of the Big Bang, the entire observable universe was, in principle, accessible to any future observer. As the cosmos ages and expansion accelerates, the accessible portion shrinks. Galaxies gravitationally bound to our local group will remain accessible for tens of billions of years, but the more distant galaxy clusters and superclusters are already effectively beyond reach and moving further beyond it with every passing year. This is not a future concern on any human timescale. On the scale of the next few thousand years, it changes nothing practical. But on the scale of millions of years, the timescale on which a truly long-term civilizational expansion would unfold, the choices humanity makes about how and how aggressively to expand will directly determine how much of the universe ever becomes accessible to life originating from this planet. The complete picture of how far humans can go is organized around three concentric boundaries. The innermost is the practically accessible universe, the region reachable with technology humanity could plausibly develop within the next century. Currently, this encompasses our solar system and possibly the nearest few star systems, if and when advanced propulsion is developed. This boundary is limited only by engineering, not physics, and expands as technology improves. The second boundary is the theoretically reachable universe, everything accessible in principle to a spacecraft capable of achieving sufficiently relativistic velocities given time dilation's gift. Under a continuous 1G acceleration profile with ideal propulsion, this encompasses the entire Milky Way, the local group, and a region extending tens of millions of light-years in every direction. Vast beyond any human frame of reference, though a tiny fraction of the observable universe. The third and absolute boundary is the cosmological event horizon, set by dark energy at approximately 16 to 17 billion light-years in every direction. Beyond that limit, nothing originating from Earth can ever go, regardless of technology, regardless of time, regardless of any other consideration. This is not a temporary limit waiting to be overcome by a clever enough engineering solution. It is a permanent geometric feature of an accelerating universe, the horizon beyond which space expands away from any origin point faster than anything can follow. 3 boundaries, 3 different kinds of limit. Only one of them is absolute. Between the theoretically reachable universe and the cosmological event horizon lies the most poignant category in cosmology, the observable but permanently unreachable universe. The observable universe, the sphere from which light has had time to reach Earth since the Big Bang, is approximately 46 billion light-years in radius. This seems paradoxical. How can we see objects 46 billion light-years away if the universe is only 13.8 billion years old? The answer is expansion. The space between us and those distant sources has stretched during the time their light was travelling, so the sources were much closer when they emitted the light we now detect than they are at the moment we receive it. Many of these observable galaxies already lie beyond the cosmological event horizon, receding faster than light, unreachable forever. We can see them. We can receive their ancient emissions, but we cannot send anything to them. They are visible across an unbridgeable distance, like watching a ship that has already passed over the horizon, knowing it is gone, knowing no ship you send will ever find it. What does all of this mean for actual human beings, for the real people who might, in some future generation, commit their lives to crossing the interstellar void? The physics of special relativity offers the gift of time dilation. The emerging engineering offers preliminary versions of the ladder needed to access that gift. Between them lies a vast middle territory that deserves direct examination. The lived experience of an interstellar voyage and what it would demand of the human beings who undertook it. The physics tells you that a voyage to Proxima Centauri could take 7 months and crew experience time at 99% of the speed of light. What the physics does not specify is how to keep the crew alive and functional during those 7 months, how to protect them from the lethal radiation environment of near light speed travel through the interstellar medium, how to design a spacecraft to withstand conditions with no terrestrial analogue, and how to sustain human beings psychologically through an experience that has no precedent in the entire history of our species. The physics gives you the destination. The engineering and the human science give you the vehicle and the people capable of surviving the journey. The energy requirements for a crewed interstellar mission, even accepting the physics at face value, are concrete and formidable. Consider a spacecraft of relatively modest dry mass, 100 tons, including life support, hull, instruments, crew accommodations and propulsion hardware, travelling to Proxima Centauri at 90% of the speed of light. The kinetic energy required to accelerate this mass to 90% of light speed is approximately 4,300 petajoules. Current total global energy production from all sources amounts to approximately 600,000 petajoules per year. So the energy needed for this mission equals roughly 7/1,000ths of 1 year of global energy production, assuming perfect efficiency. That sounds more feasible than expected, until you account for real propulsion systems operating at nowhere near 100% efficiency, and the fact that the propellant needed to store and deliver this energy adds mass that itself requires energy to accelerate, exactly as the Kolmogorov-Ski equation demands. The actual energy requirements for a crewed interstellar mission are orders of magnitude larger than the naive estimate suggests, and dwarf anything human civilization currently produces. The crew itself presents challenges entirely separate from the engineering. Human beings evolved under conditions of 1 g of gravity, a moderate radiation environment, day-night cycling, varied sensory stimulation, and complex social environments. Long-duration spaceflight violates all of these conditions simultaneously. Studies of astronauts on International Space Station missions of 6 to 12 months document predictable physiological degradation. bone density loss of 1 to 2% per month in weightlessness, cardiovascular deconditioning, vision changes from elevated intracranial pressure, and immune system alterations. On missions lasting years or decades, even with time dilation compressing the subjective journey, these effects represent fundamental challenges to crew health. The 1G continuous acceleration profile addresses the gravity problem by providing constant artificial gravity through thrust, but it requires a propulsion system of extraordinary reliability maintained for years or decades without any possibility of outside repair. There is no road service in the interstellar medium. A propulsion failure on a continuous thrust interstellar mission during the deceleration phase has no recovery option. The crew would overshoot their destination and continue into interstellar space forever. The radiation environment of interstellar space presents threats that in some respects are more immediately pressing than propulsion reliability. Within the solar system, astronauts receive partial protection from the Sun's magnetic field, the heliosphere, which deflects a significant fraction of incoming galactic cosmic rays. On the International Space Station, astronauts absorb radiation doses approximately 6 times the annual limit considered safe for the general population. On a Mars transit outside the heliosphere for months, the dose rises further. On an interstellar mission at relativistic velocities, the radiation problem worsens in 2 compounding ways. First, beyond the heliosphere, there is no magnetic shielding whatsoever. Second, a direct consequence of relativistic travel, at 99% of the speed of light, the sparse hydrogen atoms of the interstellar medium strike the spacecraft with kinetic energies comparable to high-energy cosmic rays. Each atom encountered at near light speed delivers a radiation hit to anything in its path. Shielding against relativistic hydrogen atoms requires material thickness and density that would add enormous mass to any already massive spacecraft. The radiation shielding requirements of relativistic interstellar travel remain an unsolved engineering problem without a clearly workable solution. The interstellar medium also presents a physical hazard that becomes lethal at relativistic speeds: dust. In addition to sparse hydrogen, interstellar space contains microscopic particles of silicate and carbon compounds ranging from nanometers to micrometers in diameter. At relativistic velocities, these dust grains strike the spacecraft leading surfaces with energies comparable to small explosive charges per gram of particle mass. A single sand grain-sized dust particle encountered at 99% of the speed of light delivers energy to the spacecraft comparable to a small bomb. Over the 4 light-year crossing to Proxima Centauri, even at the very low dust densities of the interstellar medium, the cumulative damage to any unprotected leading surface would be catastrophic. Proposed countermeasures include electromagnetic deflectors, magnetic or electric fields designed to push charged particles off the spacecraft's trajectory, and shape sacrificial shields of dense material at the spacecraft's bow. Both approaches add mass and complexity to an already massively complex mission profile. The interstellar medium that appears effectively empty at human scales becomes a serious engineering obstacle at the velocities that make interstellar travel possible in human lifetime terms. The psychology of an interstellar voyage has received less quantitative analysis than the physics and engineering, but it may be as challenging as any technical problem. Consider the crew's lived experience. Perhaps 6 to 20 people confined in a volume comparable to a large house, travelling in near total darkness with zero possibility of emergency resupply or rescue, and communication delays growing from hours to years as the mission proceeds. Any message sent home travels at the speed of light. 4 years to reach Earth from the Alpha Centauri system, 8 years for a round-trip exchange. The crew is isolated from all of human civilization in a way no previous human expedition has experienced. Studies of Antarctic winter-over personnel, submarine crews on extended deployments, and isolated habitat experiments give partial insight into long-term small group confinement. They consistently show that interpersonal conflict, psychological degradation from monotony and isolation, and the erosion of motivation over extended periods are genuine and serious challenges. These require careful crew selection, mission architecture, and psychological support systems that do not yet exist in their optimal form. The engineering challenges of interstellar travel are enormous. The human challenges may be equally so. Induced hibernation is one potential partial solution to the crew endurance problem. Artificially reducing crew metabolism to dramatically slow all physiological processes during extended quiescent portions of the voyage. Nature provides precedents. Bears and certain other mammals enter torpor states in which metabolic rate drops by up to 95%. Medical research demonstrates that human body temperature can be safely reduced to approximately 30 degrees Celsius from the normal 37, with patients tolerating therapeutic hypothermia for hours to several days. Extending this to weeks, months, or years requires solving numerous biological problems. Cellular damage from sustained hypothermia, muscle atrophy during extended inactivity, immune function suppression, and the neurological effects of prolonged reduced brain activity. The European Space Agency has funded research programs specifically exploring human torpor for long-duration spaceflight. Early results are cautiously encouraging regarding short-duration induced hibernation. The technology needed to sustain human beings in safe hibernation for months or years does not currently exist, but it does not appear to violate any known biological principle. It is a genuine engineering research direction, not a fantasy, of the kind that systematic effort has historically tended to resolve. For missions too long even for extended hibernation, the generation ship concept has been seriously proposed and analysed. Generation ship is a spacecraft large enough to house a complete functioning community across multiple human generations. People would be born, live complete lives, and die aboard it before arrival at any destination. Physicist Frédéric Marant's quantitative studies on minimum viable crew sizes for multi-generational interstellar voyages estimate that several hundred to a few thousand individuals are required to maintain sufficient genetic diversity and social stability across the mission duration. Such a vessel would need complete agricultural capability, medical and reproductive infrastructure, comprehensive educational system, self-maintaining manufacturing capability, and governance structures capable of functioning autonomously for centuries without external authority. The greatest challenges of a generation ship are not physical but social, motivating people born in space who never chose to depart and will never arrive at the destination, to maintain complex critical systems their entire lives, for a destination that is only ever a concept to them. These are not physics problems, they are civilization problems, and history suggests they may be the harder ones to solve. And communication constraints on interstellar missions deserve direct treatment because they are often underestimated. At the speed of light, the absolute maximum for any signal, a transmission from a spacecraft at Alpha Centauri takes 4.24 years to reach Earth. A reply takes another 4.24 years, 8.5 years for a single exchange. For Barnard's star at 6 light years, the round-trip delay is 12 years. For TRAPPIST-1 at 40 light years, 80 years. Beyond about 25 light years, Earth-to-ship communication ceases to function as anything resembling dialogue or mission support. It becomes correspondence between civilizations separated by time as much as by space. The mission designers who established the objectives may be dead before the crew receives a reply to its first status report. Any interstellar crew beyond the nearest few star systems must be prepared, philosophically, psychologically, procedurally, to function as a completely self-governing entity with no meaningful connection to the civilization that built and launched them. The mission is not guided from Earth. It is guided by the people aboard and the principles they carry with them. The case for sending robotic probes first is one the interstellar propulsion community has broadly accepted. Robotic probes require no life support, tolerate radiation environments lethal to humans, can hibernate for decades if necessary, can be made far smaller and lighter than crewed vehicles, and face no psychological or social challenges. A robotic precursor to the Alpha Centauri system could arrive decades before any crewed mission would be feasible, fully characterize the target system, mapping planets, assessing atmospheric compositions, measuring stellar wind environments, and transmit detailed findings back to Earth. This intelligence would be invaluable for designing a crewed mission to succeed in the actual environment rather than the anticipated one. The counter-argument is that robotic probes, however sophisticated, are bounded by the intelligence and scenario planning built into them before departure. While human crews can respond adaptively to genuinely unexpected conditions that no pre-departure planning anticipated, both arguments are valid. The realistic planning sequence almost certainly places robotic missions first, crewed missions later, separated by a substantial time margin in which humanity develops both the propulsion technology and the destination knowledge needed for a crewed crossing to have a realistic chance of success. Before any crewed interstellar mission is possible, humanity must demonstrate the capabilities to survive long-duration deep space travel within the solar system. Mars is the canonical next step. A crewed Mars mission at current technology requires approximately 6 to 9 months of transit each way, with a surface stay of roughly 500 days waiting for the next favourable orbital alignment for a total mission duration approaching 3 years. This would expose the crew to radiation doses significantly exceeding current ISS mission limits, to the physiological effects of months of weightlessness, and to Earth communication delays up to 24 minutes one way at maximum distance that provide a preview of the information isolation any interstellar crew would face. The challenges of a Mars mission are a dramatically gentler version of the interstellar challenge. How humanity solves those challenges, shielding, crew health, in situ resource utilization, governance, long-term life support closure, will build the technology, knowledge, and operational experience base from which interstellar missions can eventually be designed. Mars is not a destination competing with the stars for humanity's attention. Mars is where humanity acquires the skills the stars will require. The James Webb Space Telescope, operational since 2022, may answer some of the most fundamental questions about interstellar destinations before any probe or crew attempts to reach them. JWST can analyze exoplanet atmospheres by measuring how starlight filters through them during planetary transit, detecting the spectral signatures of specific molecules. The telescope is calibrated to detect water vapor, carbon dioxide, methane, oxygen, and ozone. The simultaneous presence of oxygen and methane in a planetary atmosphere would be an extraordinary biosignature. These gases react with each other and must be continuously replenished by biological processes to coexist in significant quantities. If JWST detects a strong biosignature in a habitable zone world within the next decade, the implications for interstellar mission planning would be transformative. The destination would change character entirely, from a physical environment of uncertain properties to a world where life almost certainly exists. That changes who would want to go, why they would go, what the mission would attempt to accomplish, and how all of human civilization would relate to the decision to commit the resources required. The telescope launched in Twen may answer, within years, the question that has motivated the entire project of interstellar thinking from the beginning. Step back from the engineering, from the propulsion systems, and radiation environments and generation ships, and consider the full scope of what this survey reveals about the human situation. We began with a stark question: how far can humans really go? The answer has multiple layers. The first layer is discouraging. With current technology, we cannot reach any other star within any human timescale. The second layer is genuinely encouraging. Special relativity contains a real physical mechanism, time dilation, that compresses the traveller's experienced time to human scale at sufficiently high velocities, making apparent distances manageable. The third layer is sobering. The velocities required are far beyond current engineering, and every aspect of an actual interstellar mission presents profound challenges. The fourth layer is hopeful. None of the engineering challenges violate physical law. The fifth and deepest layer is philosophical. Whether humanity develops interstellar capability is not a physics question at all. It is a question about what kind of civilization humanity chooses to become, what it decides to treat as important, what it decides to build, and how long it is willing to sustain the effort required. Carl Sagan, who spent decades thinking rigorously about the long-term future of intelligence in the universe, argued that space exploration, ultimately including interstellar travel, is not merely desirable but existentially necessary for our species. His reasoning was not romantic, it was actuarial. A civilization confined to a single planet faces a non-zero probability of extinction per century from asteroid impact, supervolcano eruption, climate catastrophe, pandemic, or the eventual expansion of our sun into a red giant that will render Earth uninhabitable in approximately 5 billion years. A civilization distributed across multiple solar system locations has dramatically better survival odds. A civilization established across multiple star systems is effectively immune to any single catastrophic event. Sagan's case for interstellar expansion is a cold calculation about extinction risk and civilizational resilience. Interstellar travel is not the indulgence of curiosity or the satisfaction of ambition. On a sufficiently long timescale, it is the minimum requirement for the continuation of everything humanity has ever created, discovered, or become. The stars are not just destinations for explorers, they are the insurance policy for the entire project of human existence. There is a dimension of interstellar travel rarely discussed in technical treatments: the temporal displacement it imposes on travellers. Consider a crew departing Earth for the Pleiades at 99.9% of the speed of light. The journey takes 444 years in Earth time. The crew experiences 20 years. They complete their mission and return. Their round trip in crew experience time 40 years. In Earth time nearly 900 years. They step off the ship to find that their departure occurred before the founding of the United States, before Isaac Newton published his laws of motion, before the printing press was invented. The civilization that built their ship has become something entirely different. The language may be barely recognizable. Everyone they knew belongs not just to the past, but to a historical era 9 centuries removed. They are temporal exiles, individuals displaced centuries from their own time by the physics of a journey they completed. The ethics and psychology of this form of temporal dislocation have no precedent in human experience. The explorers of the deepest future will be not merely physical pioneers, but travellers in time, returning from a past that no living person remembers. The mathematics of temporal exile become more extreme at higher relativistic velocities. A crew departing Earth for the galactic centre at 99.99% of the speed of light, with a Lorentz factor of 70, experiences approximately 11 years of personal time for the one-way journey. A round trip takes about 22 years of their personal experience. On Earth, 52,000 pass. The crew returns to find that their departure preceded the end of the last ice age, predated cave paintings, predated the agricultural revolution. The accumulated 22 years of personal experience spans more Earth time than the entire documented history of human civilization, multiplied by 10. This is not an abstract thought experiment about the oddities of physics. It is a precise description of what special relativity actually permits and actually requires of anyone who attempts a deep interstellar crossing. The universe permits one-way time travel into the future. It does not permit the return to one's own era. Anyone who crosses the galaxy is, in every meaningful sense, a traveller into a future they cannot predict, cannot escape, and cannot share with anyone who knew them. The question of who would undertake such a journey, knowing what they relinquish and what they accept, is one that the history of human exploration suggests will answer itself when the technology and the circumstances align. Every major expansion of the human frontier has found people willing to accept conditions that contemporaries considered extreme or irrational. Polynesian navigators crossed the Pacific in open canoes guided by stars and wave patterns, accepting risks and uncertainties that most of their world would have considered prohibitive. The first transatlantic sailors accepted months at sea, the possibility of the world ending at an undiscovered edge, and the certainty that some companions would not return. The acceptance of risk for the possibility of discovery is not a pathology. It is one of the most consistent features of human character across every culture and every historical period. The interstellar version of this drive is not categorically different from what preceded it. It is simply the version asked at the scale of the cosmos, the same ancient human question, how far can we go, addressed at the universe's actual scale rather than at the scale of an ocean or a continent. The honest accounting at the end of all this physics, engineering, and human implication is this. Humanity currently possesses the ability to reach other planets and to send robotic probes to the solar system's outer edges. We do not possess the ability to reach another star within a human lifetime. The gap is real, substantial, and not closable by any technology in current existence. But the gap is not a wall, it is a distance. And distances, given the right vehicle and sufficient commitment, are traversable. Between where we stand and the far side of the gap lies a sequence of specific identifiable engineering challenges: fusion propulsion, radiation shielding, long-duration life support, hibernation technology, autonomous AI navigation, and a suite of human physiological and psychological solutions that do not yet exist in their necessary form. Each of these challenges is physically solvable. Each is under active investigation by serious researchers. The timeline is genuinely uncertain. The outcome is not guaranteed. But the path from here to there is not imaginary. It is identifiable, it is real, and given sufficient civilizational commitment, it is traversable. Not yet, but traversable. Einstein's true legacy for interstellar travel is not the speed of light limit most commonly invoked when his name appears in this context. Yes, special relativity forbids any massive object from reaching the speed of light. But more fundamentally, it reveals that the universe is structured differently than our intuitions suggest. That time and space are not the fixed, universal background we experience them to be, but are flexible, observer-dependent, and geometrically integrated in ways with profound consequences for what is achievable. The same equations that appear to prohibit interstellar travel by capping velocity below light speed are the equations that deliver the traveller's gift of time dilation. Einstein did not build a wall between humanity and the stars. He built a map, a difficult map, with a hard outer boundary at light speed, but a map that shows the routes that actually exist within the laws of the universe. Routes that the naive reading of the speed of light limit misses entirely. The cosmos is not a featureless prohibition. It is a geometry with real opportunities hidden inside it. Opportunities only visible to those who read the geometry correctly. Tsiolkovsky's rocket equation, which we began this story treating as an apparent verdict against interstellar travel, turns out to contain the same duality as Einstein's relativity. The equation is not a prohibition. It is a precise description of the relationship between propulsion efficiency, fuel mass, and achievable velocity. It is a verdict against chemical rockets at interstellar scales, but it is also the starting point from which every propulsion improvement can be precisely mapped. Every advance in exhaust velocity, from chemical to ion to nuclear to fusion to antimatter, can be evaluated against the equation to determine exactly what new velocities and mission profiles become possible. The equation of despair is simultaneously the equation of engineering progress. The gap between chemical propulsion and interstellar travel is real. The path from one to the other, running through fusion propulsion and beyond, is not blocked by any law of physics. It is blocked by engineering challenges that time and systematic investment can, in principle, overcome. The rocket equation told us what was impossible with what we had. The same equation, applied to better energy sources and better propellant, will eventually tell us what becomes possible with what we build. The people who will achieve interstellar travel have not yet been born. This is almost certainly true even under the most optimistic projections of technological development. Fusion propulsion systems capable of reaching a few percent of light speed are probably at minimum decades away. Systems capable of reaching 10 to 20% of light speed are more likely a century or more in the future. The propulsion that could make 1G continuous acceleration interstellar travel physically achievable, providing the full compression of extreme Lorentz factors, may be centuries or millennia from now. The people who will commission the first interstellar mission, who will design its architecture and select its crew, are not yet born. The people who will board that vessel and make the crossing may be many generations beyond those designers. Interstellar travel is not a project of this decade or this century. It is a project of human civilization across multiple generations, a project requiring its beginnings long before its completion, so that the final steps can be taken by people who inherit a foundation already built by those who came before them, but not yet is profoundly different from never. And this distinction matters more than anything else that can be said about the question. The history of technology is a continuous record of goals that appeared impossible at the moment they were proposed, that subsequently were achieved through systematic application of human ingenuity to problems that physics confirmed were solvable. Heavier-than-air flight was declared impossible by respected scientists in the years before Kitty Hawk. Moon landing was considered science fiction until a decade before it happened. Genome sequencing required instruments that had not yet been invented. Net fusion energy gain was pursued for 70 years before being demonstrated in December 2022. Each of these achievements arrived not through luck or magic, but through determined, methodical engineering of problems that the underlying physics had confirmed were not prohibited by nature. Interstellar travel is not different in kind from these achievements. It is different in scale and timeline, dramatically so, but it belongs to the same category, a goal that physics permits and that engineering has not yet reached. The entire history of human technology is the history of closing exactly this kind of gap. There is something worth noting specifically about the historical moment at which this question is being asked. In the entire history of our species, 300,000 years of anatomically modern humans, we have had the ability to think seriously and quantitatively about interstellar travel for less than 1 century. Tsiolkovsky's rocket equation was published in 1903. Special relativity arrived in 1905. The first orbital spacecraft were launched in 1957. The serious physics-grounded engineering study of interstellar propulsion has been underway for barely 6 decades. Fusion ignition was demonstrated for the first time in December 22. JWST has been taking exoplanet atmospheric data for only a few years. We are, in the deepest sense of that phrase, at the very beginning. In the context of a technological civilization that might persist for millions of years, the first century of rigorously examining this question is also the century in which every foundational enabling technology — fusion energy, precision lasers, relativistic physics, computational modelling, advanced materials science — is being assembled for the first time. We are not at the end of something, we are at the end of the beginning. Tonight, if skies are clear where you are, step outside and find a star. It might be Sirius, the brightest star in the sky, a blue-white giant 8.6 light-years away, its light having travelled approximately 8.5 years to reach your eye in the exact moment you look up. It might be Vega, 25 light-years distant in the constellation Lyra. It might be Capella, 43 light-years away in Auriga, or Arcturus, 37 light-years away in Boötes, warm and orange against the dark. Whatever star you find, hold its light-year distance in your mind, the actual number of years that light has spent crossing the void between that star and your eye in this moment. And then hold alongside it everything this examination has covered: the rocket equation that makes chemical propellant insufficient, the Lorentz factor that makes relativistic travel transformative, the engineering challenges that are real but not physically prohibited, the cosmological event horizon that sets the universe's final outer boundary, and the vast, extraordinary territory between our present limitations and that absolute limit. One star, one number in light years, the entire scope of the question, contained in a single act of looking up. Somewhere in the future, not in the near future, but in the future belonging to generations not yet conceived, a person will stand at the launch point of the first interstellar mission and experience something no human being has ever experienced. They may stand on Earth, or on Mars, or in a space habitat in the outer solar system that does not yet exist. The ship they board may be fusion-powered or laser-propelled, or driven by some technology not yet imagined in any form. The destination may be Proxima Centauri or Alpha Centauri E, or Epsilon Arid Arni, or a world whose habitability was confirmed by an observational campaign that has not yet begun. Every specific detail about that departure is unknowable from here. What is knowable is that the physics permits it, that the engineering challenge, while enormous, violates no physical law, and that the impulse that will carry that person to that launch point is the same impulse that has carried explorers to every edge of the known world throughout the entire history of our species. What is knowable is that they will be standing there in some meaningful sense, because people alive today chose to begin the work that made their voyage possible. The Parker Solar Probe continues its elliptical dance around the Sun, swinging in close on each perihelion pass and reaching its extraordinary peak velocity of 430,000 miles per hour. It is the fastest thing humanity has ever built. It is performing exactly the mission it was designed to perform, sampling the solar corona, measuring the solar wind, transmitting its findings back to Earth at the speed of light. It is not going to the stars, it was never designed to, but the data it collects, about plasma behaviour at extreme velocities, about the structure of the Sun's magnetic environment, about the solar wind that gives way far beyond the planets to the interstellar medium, contributes to the accumulating scientific knowledge base from which interstellar missions will eventually be designed. Every mission, every experiment, every measurement is part of the same long story. The Parker Solar Probe at 430,000 miles per hour is pointing in the wrong direction for the stars, but it is going in exactly the right direction for human knowledge, and human knowledge is how every journey, even the greatest ones, ultimately begins. Right now, as you read these kiln, Voyager 1 is moving through interstellar space at approximately 38,000 miles per hour, its nuclear battery slowly fading after nearly 50 years of continuous operation. The signals it sends back to Earth take more than 22 hours to arrive at the speed of light. It is the most distant human-made object in the cosmos, a small gold and aluminum machine carrying a golden record of music, images, and greetings in 55 languages, moving through a universe that, by the measure of interstellar distances, has barely registered its existence. At its current speed, it will not reach the nearest star for approximately 73,000 years. Alongside it in a different orbit, the Parker Solar Probe moves at 12 times that velocity, still insufficient, still short of what the crossing requires, still measured in what we do not yet have rather than what we do, but these are where we are today, not where we will always be. The stars are not unreachable, they are simply not reachable yet, and the word yet is where the entire future of human exploration lives.